Hi everyone, in this video we are going to learn about simple linear regression, and what we do there is we are looking to see if one predictor variable predicts an outcome or predicts a dependent variable. So we're looking to see if, and they both have to be continuous. So it's just one on one. We're trying to see if something predicts something else. So does STAR tests in elementary school predict your ACT score? Something like that. So we have two continuous data. We have three assumptions with our simple linear regression. The first one is that this is all from a random set of data. The second one is that we have normal distributions of both variables, both the x and the y. And the third assumption is that the residuals are normally distributed, and we will do that at the very end. So I want to see with my fitness data set if oxygen will predict your runtime. So the more oxygen you breathe in, does that show you that you're slower, your runtime increases, or faster, your runtime decreases? So first, I'm going to run my assumptions for normal distribution. So analyze distribution. I'm going to look at both oxygen and runtime. I put those in, and I'm looking at skewness and kurtosis. Skewness is between -1 and 1. I am good with my oxygen levels. And what about my runtime? Is it okay? It sure is. So I don't even need to look at kurtosis. So now what's next? Well, there's two ways to do this. I'm going to show you the first way. We use analyze fit y by x, and I'm going to put my predictor variable in the x, and then runtime is y. That's my dependent variable. And so this shows me a scatter plot, and this shows me the overall relationship between oxygen and runtime. So we will see that the more oxygen I use, the less the runtime is. So basically, the more you breathe in, the faster your runtime is. The less oxygen you breathe in, the slower your runtime is. Your runtime is more. Now, the regression model, we're going to do fit line, and this shows us a line. This is the best line of fit, where it is showing you, it does the math, where these residuals, it's showing that basically a residual is a fancy word for this guy, Jack. His runtime was 10.95. And his oxygen was whatever that is. Okay, we're basically saying, okay, this is a little bit off with the prediction. Based on this model, we would have predicted that he would have had about a 12.2 runtime with his amount of oxygen, but we're a little off there. And so the residual is the distance between the predicted value and what the actual value was. So if you have a line with a whole lot of lines close to the line, the dots close to the line, that means it's probably a strong predictive relationship. You know, we got a lot of dots close to the line here, but this slope didn't necessarily capture, you know, this person, Chris. You know, there's some error here because this is a little bit different than what we would have predicted. You see, he had a runtime of 8.95, but really based on our model, we would have predicted 10.2 or something. So, but this is the line that we're actually testing. And I'm basically wanting to know, does oxygen predict runtime better than just using the mean of runtime to predict runtime? All right, and so I'm going to put fit mean, and this is showing me that the mean of runtime was 10.8 or something, just by eyeballing that. And so my test is basically asking, does this model with the red line do a better job of capturing the little dots being close to it than the green line? That's what it's asking. And look, oh my goodness, definitely so, because see this residual from here, that's super big. That's a big difference. And you know, are these dots super close to the green line? No, not really. And so basically, what you're doing in regression is you're saying, which line is better? Which model is better? The green one or the red one? Now, this density ellipse thing, if I show you this, this is capturing where 95% of the data would fall, and the flatter, the more oval that it is, the flatter the oval, the tighter these residuals are. They're closer to that red part, and it's a more accurate model. And so we've done the test already when we did all the fits, and so basically what you need to report is the F value. So you're probably like, what in the world? Why are we doing analysis of variance and regression? Well, in this underlying world of things, they're related, okay? So just trust me. But what this is doing is comparing the model where oxygen predicts runtime versus the model where it's just the mean of runtime predicts runtime. And it's basically asking, are these models different? And so to know if they are, then this F value is what you would report. It is statistically significant. And you see where it says model? That's meaning the linear regression model is saying, hey, did that do a good job predicting? And it did. It really did, because this is the p-value associated with it. And so these sums of squares and mean squares and stuff, this is all kind of based on, just so you know, all the math related to how far away those dots are from the red line. It's doing the math with that. So what do we actually report? You are going to look and ignore this intercept line. Don't pay attention to it. That intercept is basically just telling you the math when you do algebra. It's just telling you, you know, the slope. The intercept would probably be right up there. Well, I don't know. I don't even go there. I don't even want to go there. But what you need to do, what you need to look at is this estimate. This is B. It's just a little b in italics, okay? And it's also called the unstandardized beta weight. Sometimes it's called the unstandardized beta coefficient. And so this is the equation we have. This is y equals, and then we have the intercept, and this is the slope, negative 0.22. That's what this is right here. So this is saying in this equation that for every 1 unit increase in oxygen, your runtime goes down by 0.22 minutes or whatever it was. That's what that means. So as oxygen goes up by 1 unit, then we could predict that someone's runtime would go down by 0.22. They get a little bit faster. So you report this beta. I'm sorry, it's not beta, it's B. It's just, well, it's unstandardized beta. You report the standard error. Now this t value, what in the world is this? Well, sometimes you might have to report this as well. And this is saying, hey, is this slope statistically significantly different from 0? Is this slope different from 0? That's what the t-test is doing. And so you would also report that this is a statistically significant predictor because I'm looking at this t and this p-value. Now something else that I would have you report is go under columns, go under and find the standardized beta. Now what this is in simple linear regression, this is basically the correlation coefficient. Like, watch this. It's kind of magical. I've got correlation, and I look, hey, what is the Pearson R correlation? It is that number. Okay, so negative 0.86, negative 0.86. And what this is, how this is different, basically what this is the Greek beta symbol. If you ever see a Greek beta symbol, it's showing the standardized beta. And again, in simple linear regression, that's the same thing as Pearson R. But this is basically is standardizing all of this. Runtime was probably measured in minutes. Oxygen is measured in some kind of oxygen capacity, but when they're both standardized, it puts them both at the same level of measurement, and is also can be interpreted as standard deviations. So basically, for every one standard deviation increase in runtime, no, increase in oxygen, there will be a negative 0.86 decrease in standard deviations for runtime. So this is interpreted in standard deviations. This is more important in multiple regression when you're comparing several variables that are measured on different levels of measurement. So, and this makes everything comparable. It's kind of putting them all on the same scale. But you would need to report beta as well. This is called the standardized beta weight. Now, you also need to say how big was this? You do that by looking at R squared. Now, R squared is right here, and it's basically that number, that standardized beta squared. If I got out a calculator and said negative 0.86 squared, this is what I would get. And this is saying that 74% of the variance in runtime is accounted for by the variance in oxygen. So it's basically saying the changes that we see in runtime is due to the changes we see in oxygen. All right, so 74% of the changes we see in runtime is due to the changes we see in oxygen. That's what that's saying. Now what do we do? Don't forget about that assumption we didn't do. Now, the only way that you can do assumptions is by using the model. So you do fit model. We're going to do the same thing. And actually, this is the one I actually really use whenever I do a simple linear regression. It just doesn't show the graph, but I felt like that was good for teaching. We've got oxygen, predicting, runtime. Okay, make sure that says standard least squares. And I go down here, and it's going to give me everything that I just went over with you. All right, and make sure I right-click that columns, then I go to standardized beta to show that. It's everything I just showed you already. But now I can find power. So let's see. Parameter power. And wow, I can be 100% sure about rejecting my null hypothesis with this. Remember, I'm only looking at this oxygen part. And then I'm going to go to row diagnostics, Durbin-Watson test. Now, you need to just probably look at your notes with this, but oh no, what happened? Hopefully you can see what I can see, but I'm going to pause it for just a second. Okay, so I'm looking at this Durbin-Watson test, and what this is doing is saying, are those residuals, those differences between the little dots and the line, are those normally distributed? And they have to be. Well, to do that, I look at this Durbin-Watson test. And so I get these numbers right here, and I'm going to also look at a p-value. There's three things that I have to look at. The first one is the Durbin-Watson number right here should be between a 1.5 and a 2.5. Is it? No. So this assumption is not met. Just so you know what else we have to look for? Autocorrelation. This number has to be close to 0. Well, what does that mean? It needs to be between a 0 and a 0.5. Is it? Yes, we're okay there. This has to be above a 0.05. Is it? No, we are not okay. So what you would do, you report all of these values and you let the reader decide if how they should interpret this data. So even though I found that oxygen was indeed a statistically significant predictor variable for predicting runtime, I probably need to look at this with caution because I do not have normal distributions of my residuals. that is how you conduct simple linear regression. I'm going to show you very briefly how you write this up. I feel like it's self-explanatory, but you can get off now if you're tired of this video. But if you want to see what I'm doing, you can stick with me for a minute. So I have my correlation write-up examples. Let me get to it. All right, so I have examples of research questions, and what my null hypothesis is basically there's no predictive relationship between X and Y. I have written on here the specifics about those assumptions, so for you to look at your notes. Okay, I have everything basically that I just said. But what you report, what do you actually report? This is an example. Please don't everybody write the same thing in their dissertation. That's going to look awful. But this is a way, this is a guide for you. So B right here, this is that estimate. This is the parameter estimate. This is the unstandardized beta weight. And where did I get that from? Right here, that number. Okay. And then this was the standardized beta weight, all right? And so basically for every 1 unit increase in class size, there's a decrease in 11 units on teacher effectiveness. Units means just however that was measured. You don't have to report Pearson-R correlation, but you can, and it should be the exact same thing as what your standardized beta coefficient was, and indeed it is, okay? You do need to report what the R squared was, and explain 87% of the variance was explained by the predictor variable. And basically the F test is saying if that number is a lot different than 0, it's basically comparing the model where we have the predictor predicting Y versus just using the mean of the dependent variable to predict what's going to be next. So there's my F test. Where do I get that from? It's just from the ANOVA table that you're used to doing with ANOVA. Right, it's just right here, 118. There's my F value, and there is my P value for the F value. All right, so that is it for simple linear regression. This is my 4th time to make the video, and I made it. Thank you. We'll see you next time.